Okay, so let's discuss rocket propulsion. Rocket propulsion is an application of momentum conservation. So let's take a look at this diagram I have. We have a rocket here, and a moment later, the rocket expelled some spent fuel, and the rest of the rocket just moves on. All right, so the rocket just does that all the time until it runs out of fuel to eject, and it stops accelerating. So in order to use momentum conservation, we need to identify a before and after collision situation. So that collision, or the reverse of a collision, which is a in explosion, is this. So imagine the spent fuel was still with the rocket, so the whole rocket with that spent fuel has a total mass m, and then a moment later the spent fuel was ejected with a relative velocity some v sub ex, exhaust, right? So then the rest of the rocket is actually a bit less heavy compared to when it was before, because it has lost some mass. So this is before both the rocket and that fuel, they're together moving at the same speed. Later, they're moving at different speeds, right? And they also have, this has a little bit less mass. This one has the rest of that mass. Okay, so let's designate the total mass as m. So the rocket with the fuel. And here we have m plus dm. I know that this doesn't sound very intuitive, because why are we adding mass? We know we're actually subtracting mass. We know we're losing mass. But the dm is taken as the increase or change of mass, which in itself is a negative quantity. So believe me, this is a little easier to handle. So let's just have in mind that dm is a negative quantity. So by adding dm, we're actually losing a small amount of mass. So this mass is negative dm. Remember, dm is negative, right? So negative dm is positive, right? So we have two separate masses. They parted their ways after the exhaust is expelled. So let's take a look at this equation here. This is the starting point. So before the separation of the rocket and this much of spent fuel, altogether the system has momentum mv. And after the separation, we have here, this is the new mass of the rocket, is a little lighter. And this is the new velocity of the rocket. It is a little faster. This dv is a positive quantity. And then this is the spent fuel, and this is that spent fuel's velocity. So let's try to understand this, because the rest of them seem a bit more straightforward. You have the total mass moving at the total speed. You have this is a part of the mass moving at slightly higher speed, the rest moving at a different speed, right? So now let's say that these two, so the rocket has this final velocity, and the spent fuel has this velocity, and the different relative velocity is called this v exhaust. So that's how fast the rocket engine can throw these exhaust fuel gas backwards. So there's a relative velocity between these two. So what this means is, if this is the velocity of the this amount, let's call that v minus dm. And v minus dm plus the relative velocity, which is v exhaust, should be equal to the v of the rocket. So that's the relative velocity, adding them together. You can also add this if you think, okay, that actually should be equal to the new velocity of the rocket. It doesn't really matter this quantity being added or not. I will later find out it doesn't really matter if it's the new velocity is related to the old rocket velocity or the slightly new rocket velocity. Anyway, so that's how this is related. And then the spent fuel's velocity, exhaust velocity, is just v minus v relative to this exhaust plus dv. Right, so we don't see that term, the dv here, for good reason. We'll see that pretty soon why that's optional. So let's use that. And momentum conservation, I'll just write the expression below the diagram. mv, that's before, and after is m plus dm. This is the new mass of the rocket, slightly less than its original mass. Then v plus dv, that's the new velocity, plus this negative dm, which is a positive quantity mass. And we have that negative dm's velocity, v minus v exhaust plus dv. And let's multiply all these terms through. So first term's mv. Now let's bring this mv down from the left side. We can subtract them away. mv, mdv, and dmv, we're used to write vdm, have the differential quantity on the right side. Then dm dv plus dm dv, and so minus dm times v, so minus vdm, minus minus, so we have a positive v exhaust dm. Then we have a minus dm dv. Okay, so these two will subtract each other out, and vdm minus vdm, okay, so they're gone. And also the dm times dv minus dm times dv, you can say they subtract away, but in reality, if you have a differential quantity multiplied by another differential quantity, that's a doubly small, that's very small quantity, and we only get to keep a single differential in any expression, such as a dv or a dm, right? So two differential quantities multiplied to each other compared to those which only have one differential quantity is much smaller. So they by themselves can be ignored. That's why either including this or not, it doesn't matter the final answer. This gets tossed anyway. So what we have here left is 0 equals mdv plus v exhaust dm. Okay, so our goal is to find this final answer, which is called the rocket propulsion formula. What it says is this is the final velocity of the rocket when all the fuel has been spent, and this is the initial velocity of the rocket. It could be a zero, could be non-zero. Imagine the rocket is fired from a spaceship, right? So it has an initial velocity. And this is the exhaust, the relative velocity. The rocket engine is able to expel the exhaust fuel. And this is the initial mass of the rocket, including the engine, everything else. And this is the final mass of the rocket. That means all the, depending on when, right? You can say, well, this is when you want to find out the final speed, how much mass the rocket still has. So we want to get to this form, and we don't. We have this one here. We have some differential quantities. In order to get rid of differential quantities, we need to integrate. But in order to integrate, the dv will need some v variables to integrate with, and dm needs some m variables to integrate with. But you have m here, not here, right? So if you are familiar with how to integrate, this may not be too hard. But if you're not, let's try to work this out. So we'll work on the left side, where there's some space. So first we'll divide everything by m. So the left side is still 0, and the right side is dv plus v exhaust 1 over m dm. And then we'll divide everything by v exhaust. So left side is still 0, and right side is 1 over v exhaust this is not V, it's a constant. Hopefully the engine performs constantly. And this is that. And then we can move one of these terms to the other side. So let's say that we move this term to the left side, so we'll carry a negative sign. So 1 over m negative dm equals 1 over v exhaust. This is a constant times dv. Alright, so now to get rid of the differentials, we'll integrate both sides. Integration is just an operation. If you do both sides, then you'll still have the equal sign. So integrate. I'll start from m initial, I'll use mi, and end with m final. I find these designations are slightly more understandable than the m and m0. I'll transition into this designation later. So I have 1 over m dm, and that corresponds to these limits for the v. So when m is at its initial mass, the velocity is also at its initial value. When m is at its final mass, the velocity is at its final value, and this is dv. Alright, so integrating 1 over m gets you a natural log of m. So natural log of m evaluated between mi and mf. And then integrating a constant 1 gets you a v. So 1 over v ex v initial final. Okay, I realize I had lost the negative sign since here, right? I should bring them down. Okay, so now to evaluate this, we have minus natural log m final minus negative, so that's plus natural log m initial, so that's the left hand side, and this is also equal to this minus that. So inside of a natural log, it should be this divided by that. And we'll use those symbols. So natural log initial mass is m naught, and final mass is m. Okay, so that's the left hand side. And then the right hand side, we have 1 over v exhaust v final minus v initial, and it's also written as 1 over v exhaust v minus v naught. Alright, so now let's equate the left hand side and right hand side, and I have natural log m naught over m equals 1 over v exhaust v minus v naught, and multiply the v naught, I get switch left and right hand side. I'm focused on getting how the velocity increases. It's going to be equal to exhaust velocity natural log m initial over m final. Okay, so that is the rocket propulsion equation. Okay, so now we have this equation. Let's do this example problem here. The example says a rocket has a mass of 1.6 kilograms, 1.2 kilogram of which is fuel. So the rocket actually only has 0.4 kilograms, and then 1.2 kilograms of fuel added to the rocket. The engine ejects spent fuel at 120 meters per second speed. So this is that VEX exhaust speed. So it is launched horizontally from rest, no friction. So at the time it has only half the fuel left. How fast is it? Okay, what is half fuel left? Okay, so half fuel left. Okay, that means Full fill is 1.2 kilograms, right? So it has come down to 0.6 kilograms. So this final mass, or we use m, is equal to 0.6 kilograms plus, okay, so 0.4 kilograms is the rocket shell in the engine, so there's a 0.4 kilograms. So the final mass is equal to 1.0 kilograms. Okay, so that's what this half fill left means. So the final mass is this. And we'll just use this top equation. And if we start from rest, then V naught is 0. So we can get V exhaust of 120 and natural log initial mass we have 1.6 kilograms, final mass 1.0 kilograms. And you can pull out your calculator and calculate this while you pause the video. Okay, so the answer is 56 meters per second. Thank you.